Okay, I think we're ready to begin now. The title of the talk is Period Mapping at Infinity. From the abstract, Hodge theory, as I think everyone knows, provides a basic invariant for complex algebraic varieties. When you have a family of smooth varieties, there's also a fairly extensive global study of how the Hodge structure on the fibers in a family of smooth varieties behaves. That's a fairly highly developed subject. Also, as the varieties acquire singularities, the Hodge structure degenerates, and the local study of how that happens is also a fairly highly developed subject, going back to the work of Catani, Kaplan, and Deligne. What has been missing from the story, in large measure, is the global study of the period mapping at infinity. That is, we know locally how it behaves. There's the nilpotent orbit theorem, the SL2 orbit theorem, limiting mixed Hodge structures, that whole story. But how those fit together globally has not really been looked into that much that I'm aware of. So that's the topic for the talk today. And some applications of this, it's really work in progress. So it's just really the applications are in their beginning stages. First will be some new global invariants of limiting mixed Hodge structures. Secondly, a generic local Torelli assumption will imply that moduli spaces are log canonical, not just log general type. There are a number of results of that kind. Log canonical is much stronger. On the more differential geometric side, there are Taylor metrics induced from Hodge theory on moduli spaces under local Torelli assumptions. And it's of interest how these Taylor metrics, their curvature, behaves globally at infinity. And finally, the story does suggest the construction of a possible toroidal compactification of the image of a period mapping. In outline, I'll first talk some about extension data, just basically reviewing definitions, basic definitions, and giving the definition of what is meant by extension data. For the basic results, there are, at this point, three. First is a removable singularity result for extension data of level 1. I'll explain what that means. Secondly is that extension data of levels 1 and 2 determines all the rest. And the third is a formula that relates the behavior of the extension data as you move along a fiber at infinity to the normal to that fiber. And again, I'll explain those terms. For applications, ampleness of a certain bundle, freeness of another bundle, asymptotics of the Ricci curvature, and the speculative toroidal completion. To begin by reviewing some basic definitions, a Hodge structure of weight n is given by a Q vector space V and a filtration of the complexification of V, a Hodge filtration as pictured there, satisfying that condition, the opposite condition, direct sum Fp and the conjugate Fn minus P plus 1 for all P is an isomorphism. That's equivalent to the perhaps more familiar Hodge decomposition. And the equivalence is written out there. If you have the Hodge filtration, then you define the Hodge decomposition by Fp intersect Fq bar Conversely, if you have the VPQs, then you define the filtration by the sum for P prime bigger than or equal to P. So that's a Hodge structure. A mixed Hodge structure has the additional data of a weight filtration W defined over Q. F is only defined over C. The weight filtration here, I'll take it to have length N. I'm thinking really of the mixed Hodge structure and the nth cohomology of a complete variety. So the condition on relating the weight and Hodge filtration is that on the associated graded, the induced filtration from the Hodge filtration gives a Hodge structure. So the associated graded of the weight filtration have induced Hodge structures from the Hodge filtration. By extension data, what is meant is the set of mixed Hodge structures, all mixed Hodge structures that have a fixed associated graded. So you fix the Hodge structures on the associated graded and look at all mixed Hodge structures with that fixed associated graded data. E sub k of the mixed Hodge structures that are in most k-fold iterated extensions. So you think, for example, a mixed Hodge structure E1 is in a short exact sequence with Hodge structures on each end and the mixed Hodge structure in the middle, and so forth. So E1 is just X1s in the category of mixed Hodge structures. It's the direct sum of the X1 of the HK comma HK minus 1s above. And that is a compact complex torus. So the extension data of level 1 is a compact complex torus. In the category of mixed Hodge structures, the higher X's are all 0. There are a lot of mixed Hodge structures. There's enough so that when you go through the definition of what's meant by the higher X, you have enough flexibility to show that those groups are all 0. The mixed Hodge structures that are in most k-fold iterating extensions, the E sub k, are fibered over the ones, EK plus 1 over EK, whose fiber is a direct sum of the X1s. Again, the X1 in the category of mixed Hodge structures of 2 Hodge structures. And you'll notice the X1 for EK plus 1 over EK, the gap in the X1 is K. So it's the extensions between 2 Hodge structures with a mixed Hodge structure in the middle, where the difference in the weights at the 2 ends is K. Those fibers are complex manifolds. They're quotients of Euclidean space by discrete subgroups, and they can be compact tori, C stars, C, some mix of those. A limiting mixed Hodge structure is a particular kind of mixed Hodge structure. You begin with a nilpotent endomorphism. From that, there's a standard linear algebra construction of a weight filtration that has length twice, basically twice the index of nilpotency of n. So it's unique weight filtration satisfying those 2 conditions there, linear algebra conditions, plus the condition that it shifts the Hodge filtration by 1. Okay, so that's a limiting mixed Hodge structure. The weight filtration has the special property that looks like a hard Lefschetz theorem, linear algebra property, and it moves the Hodge filtration by at most 1. In Hodge theory, the Hodge structures that one uses essentially always have polarizations. Polarizations will, for House, be given by a bilinear form defined over Q. That should be, the first should be V tensor V mapping to Q, not C. And endomorphism, the N, it preserves Q. And that means that the weight filtration of N has a self-duality. The annihilator of weight L is the weight 2m minus L minus 1. From the Hard-Lefschetz property, one then infers that these bilinear forms from the associated graded of weight m plus k tensor weight m minus k to q, those bilinear forms are non-degenerate. And what one finds as a consequence of this is that the associated gradeds of a limiting mixed Hodge structure are a direct sum of polarized Hodge structures. Okay. In general, we'll have not just one N, no potent N, but a collection, say R of them, commuting, and they have the very special linear algebra property that the weight filtration is the same for all elements in the interior of the cone. If you look at commuting sets of nilpotent operators, the condition to have the same weight filtration is an algebraic one, and it is a highly, the set of weight filtrations that satisfy this condition, of cones that satisfy this condition, is a very small dimension. All right. A lot of equations are involved to have the same weight filtration. The special structure for the extension data associated to limiting mixed Hodge structures, the real tangent space of the level 1, J, complexified, so that's a complex manifold. You take its real tangent space, tensor with C, and it splits into conjugate subspaces. In fact, it has a Hodge decomposition. And the Hodge decomposition is the one pictured here. It begins at k minus 1 comma minus k. And it has weight minus 1. So the sum of p plus q should always be minus 1. Sitting in the middle is the stuff of type minus 1, 0 plus 0 minus 1. All right. Looks like sort of like a tape object sitting in there. And the tangent space to J has a subcompact torus corresponding to the maximal sub-Hodge structure whose tangent space is in the bracket part. Okay. So it's like an intermediate Jacobian where you look at the stuff that's right next to the middle in the Hodge decomposition, and that gives you a compact subtorus. So this compact subtorus has the very special properties of being an abelian variety. That comes about by looking at the algebraic construction, the graded -2 of the endomorphisms. That should be Q, not G. Contains wedge 2 of H1 of the compact torus, the full torus, which is the dual of H2. And the proposition, just a linear algebra calculation, is that the integral 1-1 classes contain the dual of the cone tensor Z. And if you're in the interior of the cone, tracing through the linear algebra identifications here, you get an ample line bundle over this subcompact subtorus whose tangent space sits right in the middle two pieces of the Hodge decomposition of the tangent space of the full torus. Okay. So when you have a limiting mixed Hodge structure with a cone, then you get ample line bundles over a part of the extension data corresponding to what sits right in the middle when you take the Hodge decomposition of the tangent space to the level 1. So the basic results are these. We begin with a smooth variety. We're thinking here of, you know, a Zariski open in a complete variety, B bar, whose complement is a reduced normal crossing divisor. It's the usual picture that you have a quasi-projective smooth variety with a smooth logarithmic completion. Then there's 1-1 correspondence between variations of Hodge structure. On the one hand, that's over B, the Zariski open, with period mappings from B to quotients of period domains by discrete subgroups. The variation of Hodge structure, in the parentheses here, the script V, is the complexification of the local system given by the Gauss-Menin connection. That's the delta. That's the Gauss-Menin connection. It's a flat connection, defines a local system, and its complexification is the script V. Okay. The Hodge line bundle is gotten, and so the script F, those give you a Hodge structure on each fiber. And there's a particular line bundle that we'll come back to that's just the tensor product of the determinants of all these Hodge bundles. Okay. So one is picturing here a family of Hodge structures depending on a parameter space B. And at each point you have a Hodge structure and you have a distinguished line bundle just by taking the determinant bundle of all the subspaces in the Hodge filtration. Standard result is that local monodromy around the ZIs is unipotent, and by going to a branch cover and so on, you can assume it's quasi-unipotent, you can make it unipotent. So a neighborhood of infinity looks like a product of punctured disks, delta star to the rth power, where you have R monodromies, and some parameters, delta S. The cone is the span over the positive integers of the logarithms of monodromy. Okay. The geometric case is where you have a family of smooth varieties, script X over B, and you have a completion, X bar over B bar, that has the form of semi-stable reduction given by Abramovitz, Karu, and others. Okay. So taking the Hodge structure of the cohomology of the fibers would give you a variation of Hodge structure. Two examples to keep in mind. One is the moduli space of curves of genus G, M bar G. That's essentially smooth. Even when you have singular curves, the moduli space locally is, the Konishi space is 3G minus 3-dimensional smooth variety. On the other hand, when you go to algebraic surfaces, the Kolar, Shepard, Baran, Alexiev moduli spaces, I'm calling them here M bar. So M, script M is the moduli space, M bar is the completion. Those tend to be highly singular along the boundary. Going back to the Hodge theory picture, Catani-Kaplan-Schmidt's theorem is that if you take the period mapping, that's the thing on the right here that associates to each point the Hodge structure corresponding to that point in the period domain factored by the discrete monodromy group gamma. Catani-Kaplan-Schmidt showed that the limit as you go to the boundary is an equivalence class of limiting mixed Hodge structures where the monodromy cone is the one described on the previous overhead. Its equivalence class is two limiting mixed Hodge structures are said to be equivalent if the two ends differ by if the two Fs, the two Hodge filtrations, differ by the exponential of some complex multiple of n. Okay. So you're essentially factoring by the one parameter group generated by the exponential of the logarithm of monodromy. Then the period mapping, whose image is an analytic variety and the quotient of the period domain, that extends to P bar. And the definition of the extension is you associate to the limit point the associated gradient of the limiting mixed Hodge structure. You take just the raw, the simplest information in a limiting mixed Hodge structure, just the associated gradient, it's a direct sum of Hodge structures. And that defines on the set level the map phi E. A conjecture of some years standing is that P bar is actually an analytic variety on which this Hodge line bundle, canonically extended, is ample. In the classical case, when D is a bounded Hermitian symmetric domain, this is a consequence of the Bailey-Borel-Satake compactification. So this is some sort of Hodge theoretic analog of Borel-Bailey-Satake. Using logic, model theory, zero minimal structures, there's been recently very interesting work by Baker, Bruno Barbie, Zimmerman, and others, Klinger, that prove that the P itself, the thing in gamma by D, D by gamma, is an algebraic variety, not just an analytic variety, on which the Hodge line bundle is ample. Okay. So what's missing is what goes on at infinity. What is known is that the fibers, the set theoretic fibers of this map phi E, the set theoretic fibers are subsets of B bar, and what's known is that they are complete subvarieties. And as such, they'll lie in some minimal stratification, Zi, and along these fibers, the graded limiting mixed Hodge structures are constant locally. What is varying is the extension data. So the geometric picture is out at infinity, you have this family of limiting mixed Hodge structures. Map them to the associated graded. That gives you a map to a bunch of Hodge structures, okay? Those maps are fairly well understood. What you have not understood is what goes on globally along the fiber. Well, first, if you're on a fiber, the map to the extension data of level 1 is only defined on a Zariski open. You have to take out the intersection with the strata of lower dimensions that meet the fiber. So the first result is that actually the level 1 extension data map extends to the complete fiber. That's a result, that's a global result. It's not a local one, and it's proved using mixed Hodge theory. The reason is the following, that this BP star, take out the lower dimensional strata, is an quasi-projective, an open algebraic variety. So the H1 has a mixed Hodge structure. Now you're mapping this open variety to a compact torus, J. On the induced map on the first homology is a morphism of mixed Hodge structures. And if you think about it, the H1, the first homology of the open one, has two pieces. The first is the first homology of its completion, and the second is the zeroth homology of what you've taken out, where it meets the lower dimensional strata. Those have different weights. So the mapping on the first homology kills the mapping that comes off the stuff that you took out of the fiber. Okay? So in other words, it induces a mapping on the first homology of the complete fiber, BP. Okay? Okay. So whenever you have a map from the first homology of a complete variety to the first homology of a compact torus, that's a morphism of Hodge structures, that induces a holomorphic map of the variety itself through the Albanese variety of BP to J. So that's the reason that phi1 extends. We'll let phi-m be the map to the extension data of level m. The next result is that the phi-m's, so you're going to higher and higher level extension data, that actually you only have to go up 2 and you've determined everything. Okay. It's sort of a very surprising at first sight result that the limiting mixed Hodge structure has all these different levels of extension data in it. Why should you only have to go to level 2 to know everything? And that's what the result says proves. It's a local result using the infinitesimal period relation. It's interesting that in the classical case, when D is a Hermitian symmetric domain, you know that D can always be equivariantly embedded in the Siegel upper half space, the symplectic group by, the one with the symplectic group. So what I'm saying is that in the classical case, the universal example is a family of abelian varieties. And there, the only levels of extension data that you get from the first homology limiting mixed Hodge structure on the first homology of an abelian variety are levels 0. The mixed Hodge structure only has weights 0, 1, and 2. So you can have at most level 2 in the classical case. So in the classical case, the theorem is obvious, more or less. It's the non-classical case where it is not obvious. And what one is saying is that the non-classical case, in many ways, is expected to behave a lot like the classical case, a sort of familiar phenomenon in Hodge theory. The main result is the theorem in the box here. That says if you pull back these line bundles that are defined by elements in the monodromy cone, you pull them back by the extension data map, look at the level 1 extension data, that those are expressed in terms of the line bundles given by the divisors restricted to the fiber, okay, with some coefficients that depend on the pairing between the monodromy cone and its dual. So it relates the behavior of the limiting mixed Hodge structure along a fiber to the normal behavior to the fiber. It's worth remarking that these three results really are results about the behavior of a period mapping at infinity. The statement and the proof, all you really have to have is a neighborhood, say script U, of Z and B bar. You don't need the whole B bar. So to turn to applications, I'm going to make, for the first few, the assumption that the map to the level 1 extension data does not have any positive dimensional fibers. So phi1, so to speak, a finite map. That happens sometime, but it is a restrictive assumption. I'll come back to explain sort of geometrically when it fails. But let's just make that assumption. Okay. So then if the fiber does not meet any lower dimensional strata, then what it says is that the line bundles given by the divisors at infinity are negative along the fiber, or the conormal bundle, if you like, to Z in B bar, to all the divisors. So Z is the sum of all the ZIs. It's the divisor at infinity. The conormal bundle to that thing along a fiber is ample. So the behavior of the extension data along the fiber is telling you something about the geometry of the fiber out in the open B bar, okay, outside of infinity. It's a pseudo-convexity statement along the fiber. In complex analytic terms, to say the conormal bundle of something is ample is like saying that thing has a strongly pseudo-convex neighborhood, a strongly pseudo-convex boundary of a neighborhood. If the assumption, where did that assumption, if that assumption is not satisfied, you can still do some things. So for example, let's just take the case where the dimension of B is 2. That's a missing B there. So we're looking at the simplest case. The simplest case is when your variation of Hodge structure is over a curve. That's really well understood. So the first case where things start to get be less well understood is when you have a two-parameter family of global two-parameter family of Hodge structures. So B is an algebraic surface. You can still use that theorem on the preceding one, but I'll come back to how you use it in a minute. But let's assume that all of the branches at infinity get mapped to points. So that means that basically what is meaning is that the variation of Hodge structure does not extend over the branch at infinity. Then that result, this one here, can be used to show that the intersection matrix of the branches of the components at infinity is negative definite. And then it's well-known theorem due to Grauert and complex geometry that you can contract Z in the neighborhood U of Z. The global version is the theorem in algebraic geometry due, I think, to Mike Artin and others back in the 60s. David Mumford also has a paper on that. But the local analytic results are a result of Grauert. A global result is concerning the Hodge line bundle, that there are integers, positive, well, they're actually positive rational numbers. So this is a Q line bundle, such that L, the Hodge line bundle minus the sum of the AIs, ZIs, is ample. And you cannot choose the AIs to all be 1. You can't just say you take L and look at sections of the Hodge bundle extended that vanish on Z, that's an ample bundle. That won't be true. What are these AIs? I'll come back to this in a second, but I'll just say what they are in a minute. You have a matrix, the intersection matrix, that's negative definite, and the off-diagonal entries are non-negative. This is at the bottom of the overhead here. Okay? Any such matrix, symmetric, negative definite matrix with off-diagonal entries non-negative, has very special properties. And what these AIs are is you prove that the maximum eigenvalue of eigenvector of the matrix has strictly positive entries. That's what the AIs are. So geometrically, they're coming off of the information in the intersection matrix of this divisor Z. Okay. So in general, the uses of this main result are somewhat subtle. They're still being worked out. They're not well understood so far. And part of the reason is that when you look at what it gives you, if A is in the interior of the monodromy cone, then the degree for any curve in a fiber, curve C in a fiber, it has positive degree. But here, the first terms, where remember the i's, the n sub i's, that's the BP is in a strata Zi. There you have the conormal bundles are semi-positive. On the other hand, for the lower dimensional strata, so C is in the Zi here. For the C that meet the ZJs, the lower dimensional strata, the intersection number of C with ZJ is non-negative. So you get a different sign. So what you've gotten here is something is positive, and it's a difference of things with opposite signs. So you have to play those inequalities off against one another. So the geometry that's behind that still isn't really understood in general. Among the properties this line bundle over a smooth, complete variety can have are nef, big, those are numerical, free, and ample. Those are geometric to me because they give you a geometric object. A free line bundle is coordinate ring, the ring of powers, of global sections of powers is finitely generated, so you can take Hodge and you get a variety. The Hodge theory abounds with literature with results of the first two types, nef and big. But those of the second type are more scarce. They're harder to get at. And I think one reason, at least for me, is that you haven't really used global information along these fibers of the period map at infinity. So to give an example of how that can be used, that global information, we recall the Higgs bundle construction. You just take the successive quotients of the Hodge vector bundles, take their direct sum. You take the map from EP to EP minus 1 tensor omega 1 induced by Gauss-Manin. Delta squared equals 0 is equivalent to theta wedge theta is 0. So that's a Higgs data, the vector bundle E and the endomorphism or the map theta. And if we have a period mapping or a variation of Hodge structure, this theta induces a map from the tangent bundle to the endomorphisms. That's the map induced by theta. And it's of Hodge filtration minus 1. It drops the P from P to P minus 1. So on our global picture where we have a complete variety B bar with a divisor Z, you have the Higgs mapping, the delta, that this is just a cup product. It's got induced by the Gauss-Menin connection, okay, which has a logarithmic pole along Z. Okay. The local Torelli assumption I'm going to make is that this map is 1-1. It's an inclusion of bundles. And then three things happen. The first is that assumption that the level 1 maps phi1 are finite, that is satisfied. The second is that the canonical of B bar plus Z is free. And the third is, okay, once something is free, you can say, is it ample? And the third is that it's ample if and only if the Gauss map of the phi1 has no positive dimensional fibers. Remember that phi1 is a mapping from this fiber B sub P. That's where the associated gradient of the limiting mixed Hodge structures are constant. So it's mapping those to the level 1 extension data, which is a compact complex torus. Whenever you have a map of a variety to a complex torus, you have the associated Gauss map. You take the induced map on tangent spaces and translate all the tangent spaces to the identity of the compact torus. That maps you to a Grassmannian, and that's the Gauss map. So what one is seeing here then is that the canonical plus Z is free, and it's ample if and only if this geometric condition is satisfied. An example of case B, where it's free but not ample, is the classical case of abelian varieties, principally polarized abelian varieties of dimension G. Then the Satake-Bailey-Burrell, the fibers themselves are abelian varieties, and the map feeds, the level 1 it should be, is the identity. So the canonical plus Z is actually the pullback of the bundle on Satake-Bailey-Burrell given by the line bundle given whose sections are automorphic forms, pulls back or automorphic forms of weight 2. Okay. So in the classical case, the K bar B plus Z is the automorphic form line bundle. In the non-classical case, it can be ample. Turning to the Ricci curvature, we look at the Chern form of the extended Hodge line bundle. That gives a complete Kähler metric on B. So one would like to know its geometry. And the geometry is that the Ricci form, so that's the minus the Ricci curvature, is the Chern form for the canonical bundle of B bar. That is bounded both from below by the Chern form of the Hodge line bundle and from above by the Chern form of the Hodge line bundle plus a term sigma. Sigma is what's called a second fundamental form in Hermitian differential geometry. It's the second fundamental form of the subbundle given by the image of the map at the bottom there. That gives you a subbundle of a Hodge type bundle. And anytime you have a holomorphic vector bundle, Hermitian holomorphic vector bundle, with a subbundle, there's what's called a second fundamental form. That's what this sigma is. Sigma is positive, it has a sign. Second fundamental forms always have a sign. And it's positive if the Gauss map is finite. Okay. So what this is telling you is something about the asymptotics of the Ricci curvature of this complete Kähler metric. Finally, with some details still to be checked, Another result is that if this local Torelli assumption is satisfied only at a general point, remember the local Torelli assumption was that this mapping should be injective. Suppose it's just injective at a point. What that's saying is that the image of the period mapping is the same as the dimension of B, that it's an equidimensional map. Okay, it can blow down stuff, be branch covers and so forth, but it should map to something of the same dimension. So if it's satisfied at a general point, then there's an L naught and a K naught depending on L naught, so that the K times LE minus L naught Z is free. Okay. So the details here have to do with sort of technical details about how the fibers of this extended period map, how the fibers relate to each other. They can be, if it's a smooth fibration, this theorem is proved. If it's not a smooth fibration, then you'll have stratification where on the strata it's smooth fibration. You need to know how those strata themselves fit together. That's the missing technical issue. If that's settled, then you get freeness of this bundle. And that would give a sharpened version of this earlier result, the Baker-Bruno-Barbie to Zinnerman result. They assumed that the monodromy gamma is arithmetic. One knows that there are many examples where the global monodromy is a thin matrix group. It has infinite index in the corresponding arithmetic group. The volume of D by gamma is infinite. And there are many geometric examples now where this happens. And so one would like to get rid of that assumption. Finally, just some speculation on the question, what would be the natural completions of the images of period mappings? And I think what Hodge theory, so natural by the completions of images of period mappings, by definition, that means we're looking at Hodge theoretic stuff. So the simplest completion is Satake, Bailey, Burrell. You just toss in all the associated graded of the limiting mixed Hodge structures. That was called phi sub E earlier, the E for extensions, call it phi naught now. Next, okay, we'll toss in the level 1 extension data together with the associated graded of the limiting mixed Hodge structures. Okay. And then phi 2, you toss in levels 1 and 2, and you can keep going. The earlier result, theorem B, says that the phi m's for M3 or bigger are determined by phi naught, phi 1, phi 2. Okay. And determined here, one has to be a little careful what it means. It means determined up to some constants, like integration constants in calculus. And the meaning, geometric meaning of those, they have arithmetic meaning, actually. They're kind of interesting. If you look at the first non-trivial case, you're getting conductors, the sorts of things that arise in number theory. So they have interesting geometric and arithmetic meaning. Anyway, the candidate for the natural completions, the candidates just at the set theoretic level, are the images of phi naught, phi 1, and phi naught, phi 1, phi 2. Those would be some sort of toroidal completions of the images of period mappings. I say toroidal for the following reason, that if you look at phi 2, what phi 2 maps the fibers of phi 1 to is products of C stars. The simplest example here, I'll just describe it verbally, is picture of a family of curves of genus 2. Sort of the first interesting example you come to. The first thing that can happen is the curves acquire a node. Okay, that's the first level in moduli. So the normalization is an elliptic curve that has 2 points on it that are identified to create the node. The next level is the curve acquires 2 nodes. Okay, that's the Riemann sphere, P1, with 2 pairs of marked points on it. Okay, and there's a cross ratio there. Okay. So what about the extension data in the limiting mixed Hodge structure where you have curves of arithmetic genus 2, geometric genus 0, 2 pairs of marked points that are identified to give 2 nodes? Okay, there the phi1 is trivial, there's no j. But phi2 is not, it's the cross ratio. That's a point in C star. And to complete phi2, you simply let the nodes come together. So the 4 points cease to be distinct in some way. That's a toroidal completion of C star. That's the sort of flavor of what's going on when you try to complete this map phi2. That's the reason for using the word toroidal. But also, you would say, well, also you've got these monodromy cones floating around. That begins to sound like toroidal stuff also. Those monodromy cones have really special properties. They have the property that the weight filtration is independent of the point in the cone. And if you look at the faces of the cone, there's what's called the relative weight filtration property. That's, again, a very special linear algebra property. So toroidal here is not going to be sort of general toroidal, but it's going to be toroidal where the cones have special properties. That, so far, has not really been, certainly not been worked out, and in fact, is not at all understood. I think it's a very interesting issue. And this is just going over what I said. The bottom there is a slightly more precise statement that phi2 maps as a Zariski open to something like a product of C stars. And these are some references. Thank you. There are questions? Hodge theory is important to PDE. I think PDE is important to Hodge theory. You know, the basic theorems that underlie Hodge theory require PDE. And PDE, the classical Hodge theory, the PDEs are linear. In non-abelian Hodge theory of Simpson and all, they are nonlinear, they're Yang-Mills type PDEs. So the answer is certainly that PDE it's not only important, but it's crucial for Hodge theory.
Well, let's thank Professor if there is no more questions. Well, thank you very much, Professor Griffiths. Thank you very much for this very nice talk.